Hi, I'm Romain Loiseau, and I'll present our work entitled Learnable Parser, Discovering 3D Prototypes in Aerial Scans. To analyze 3D aerial LiDAR scans, most methods either require expensive 3D annotations or, for unsupervised approaches, rely on abstract feature representations that are difficult to interpret. Furthermore, most of these methods are often designed, trained and tested on synthetic or highly curated data. In this paper, we introduce an unsupervised framework for parsing large real-world 2D scans into interpretable parts, alongside a new uncurated, annotated aerial LiDAR dataset acquired in various environments. To perform semantic and instance segmentation directly through reconstruction, we learn 3D prototypes alongside a way to deform and position them to reconstruct inputs. Our 3D prototypes are point clouds whose point positions are directly learned as free parameters of the network. Alongside these learned prototypical point clouds, we will also learn neural networks to select, deform, and position the prototype instances. As you might expect, learning jointly 3D prototypes alongside a way to select, deform, and position them is particularly difficult. Firstly, we have to deal with a large variety of objects across different scenes. Secondly, it is difficult to separate objects in a scene, and each scene may have a varying number of objects. In this presentation, we will focus on dealing with ambiguous object separations and varying number of objects. In a previous paper, we showed that we can explore the content of large 3D point cloud collections by learning 3D deformable prototypes, and that the learned prototypes represent well the diversity of objects contained in the dataset. Today, our goal is to go from one object to complex scenes, to learn to decompose a scene into simpler and easier to understand components. To achieve this, we train a highly constrained model M to approximate a point cloud with a combination of learned 3D shapes. We say that we are able to reconstruct individual objects. Let's construct the full model together. To reconstruct a scene composed of numerous objects, we introduce slot models. Each of the slots will be responsible for reconstructing a specific object instance in the scene. At this point, the reconstruction model is the union of the output of all the slots. To handle variations of similar objects, we set the case output of each slot as a deformed version of the case prototype. Our model can now deform and position each prototype, but it cannot deal with varying number of objects in a scene, as it is forced to reconstruct S objects and cannot select the prototype used at each slot. To deal with this, we use a probabilistic modeling. Each slot is associated with an activation probability alpha S, which predicts whether the slot will be used in the reconstruction or not. Then, the prototype used for the slot S is determined by a random variable Bs. Finally, the complete reconstruction model is the union of the activated slots, where each slot outputs the deformed and posed select prototype. Finally, we use a probabilistic modeling of the reconstruction loss with regularizations to ensure that we learn meaningful and accurate prototypes. To evaluate our model, we introduce the Earth Parser dataset, a dataset of 7 annotated scenes acquired by aerial LiDARs in various environments. Our dataset covers a variety of urban, natural, and rural scenes, making it more representative of the diversity of possible use scenarios than comparable datasets. Trained on different scenes, our model can learn a wide variety of prototypical shapes, such as boat masts, wind turbines, and houses. These prototypes provide an immediate insight into the content of these real-world scenes. The highly constrained nature of the deformations prevents slots from repurposing the same prototypes for different objects, making the learned prototypes easy to identify and manually annotate. After annotating the prototypes, we can use the reconstruction to perform convincing semantic segmentation of complex scenes. By considering each slot as a different instance, we can also perform instance segmentation of complex scenes, such as a marina, for example. We evaluated our method against others by comparing the semantic segmentation and the reconstruction performances. Thanks to our probabilistic slot and prototype selection, we demonstrate that the Learnable parser can handle inputs with a variable number of objects using only a small set of learned prototypical shapes. In this paper, we show that our novel unsupervised methods for parsing complex real-world aerial scans provide strong semantic segmentation results, while maintaining interpretability of the model. We also introduced datasets of 7 annotated scenes acquired by aerial LiDAR in various environments designed to evaluate the method's ability to parse complex real-world scenes. To the best of our knowledge, we are the first to demonstrate the possibility of performing deep unsupervised 3D shape analysis on such a challenging real-world dataset, and we believe that our results open new perspectives for computer-assisted environmental monitoring and economic intelligence. Thanks for your attention.